Okay, so next week we're going to look at manipulating audio that we've recorded ourselves. But to start our play with audio and pure data, we're going to look at oscillators. So oscillators are kind of building block audio objects which output periodic audio waveforms that have a regular pattern, repeats over time. For example, you have a sine wave oscillator. Sine wave looks like this. So if you had you could imagine if you had a microphone recording the playback of a sine wave, the movement of the microphone would move in this way over time. So we have sine wave oscillators. We have also square wave oscillators that output digital audio that looks like this. And we have sawtooth oscillators that. So what I want to focus on this week really is what those basic oscillators sound like and how you can use them to start making some kind of nice electronic sounds in pure data. Let me make sure I've got my audio turned on down there. I think I do. First of all, I'm going to turn on digital audio. And then, as you can see, I have an object, the OSC object here, which I'm using to output a sine wave which has a frequency of 880 hertz. So 880 times a second, that same sine wave pattern is repeating. And all this patch is doing really is taking that sine wave output, we're multiplying it by 0.5 so we can make it fit nicely in this output window down here. So in other words, we're scaling it down to half its normal size, and then I'm drawing it in that output window. And what we can also do is put in a digital analog converter object down here. We can actually take the output from that oscillator and listen to what it sounds like. There you go. It sounds like a beautiful, beautiful sine wave. And I'm very glad I scaled that down by half, otherwise it would have been very, very even louder. So that's what your basic sine wave output sounds like. If I change this to be a different number, if I make it half the frequency, then we hear the same note an octave lower. But I can specify any frequency here. It doesn't have to be an A. I can pick any particular number that I like. And so there you go. So that's what a sine wave looks like and sounds like. PD also has a square wave, which is when it's moving, it's actually a bit hard to pick up what's going on. But essentially, we're moving sort of between the minimum value and the maximum value repeatedly. And depending on what frequency we set on determines how frequently it changes from the minimum to the maximum value. So if we output the square wave, I'm just going to turn the volume down a little bit. If we output the square wave, we hear that sound. If we make it a bit lower frequency, let's put it down to 220 hertz. You can get a sense of the kinds of characteristics that a square wave sound has. So that's square wave. We also have a sawtooth wave. So we use the phasor object to generate a sawtooth wave for us. Again, it actually is easier to pick up the shape of the phasor wave when it's not moving. So the phasor wave, phasor moves from a low value to a high value, sort of ramps up over time, and again how often, and then it jumps back down to the low value again. So from lowest value to maximum value, and then jump back down again and repeat over and over again at a rate that's determined by whatever argument you're passing here. So again, to listen to it. That's what it sounds like. Doesn't sound that different to a square wave, but if you listen, I'm not sure how well that's coming through on the video. There is a different characteristic to them, but they're a little bit similar. So that's sine wave, square wave, and sawtooth wave using the OSC object, the square object, and the phasor audio object, all with tildes after their name. The other useful, well, you wouldn't really call it an oscillator, but the other useful noise, sort of audio generator that PD has is noise, and you can see here that it outputs sort of basically random samples that are all over the place. So random samples between the minimum and the maximum value, and you probably all would have known what noise sounds like. If I hook this up, that's the sound of noise. And that can actually be quite useful in musical context if you want to generate the sound of, I don't know, like a snare drum or something like that. You might, if you wanted to kind of synthesize the sound of a snare drum, you might use some noise and maybe mix it with some other oscillators. So that's an important point, I guess, is that using these combinations of basic building blocks, you can actually create quite a large range of sounds. And all the original old analog synthesizers were really all about patching together different oscillators and having them mess with one another and mixing them together to make different kinds of interesting sounds. So get rid of that. Yes, now one thing to point out, you saw me in that previous patch, I had a times tilde object to scale down the oscillator, the values coming out of an oscillator, just to make the audio a bit less intense, cut down the volume a bit. So the audio stream in pure data is important to remind ourselves that the audio stream coming out of any audio object is just a big long stream of numbers. So when we're talking digital audio, we're talking stream of numbers. Very important to emphasize that. So the stream of numbers that come out of here, we can do maths on. So if we take the stream of numbers, the stream of samples coming out of the oscillator object, and multiply them by 0, then what we get out into our speakers through the digital to analog converter is going to be inaudible. We've made all the samples have a value of 0, which is silence. So I have here a sine wave oscillator. At the moment, we're multiplying the output from that sine wave oscillator by 0, so we're not hearing anything. But as I gradually bring up that, we're not hearing nothing at all. Why aren't we hearing anything? Oh, I know why. Because I've connected up the wrong audio. I've only got one audio channel connected up to my amplifier here, just for convenience. So I've actually hooked up the right outlet to my amp. So that's why I only had this connected to the left inlet. Nothing. We're not hearing anything. If I connect up to the right inlet and then bring up the slider, you'll start to hear. It's a bit glitchy, but yeah, but for reasons I won't go into, it's a bit glitchy, but we're multiplying those samples by the number coming out of this slider, which I can show you what the number is here, just for interest. So the maximum will be 1. That is the unchanged sample values coming out of the oscillator, and at the bottom, of course, we're 0, which means silence. So you can do arithmetic on your samples because they are just a stream of numbers. Another utility object that I'll point out here briefly, I don't want to go into it in great depth, is the pure data M2F object. M2F, M stands for MIDI, F stands for frequency. So if you want to play music using these oscillators, it's quite difficult, or most people don't find it very intuitive to specify the frequency of individual musical notes. They usually find it more easy to say, well, I want to play a C or a C sharp or an F or something like that. Because we're in a computer, we're still talking numbers, but MIDI is well, I think I've mentioned it before, but it's a standard for communicating between digital musical instruments. And in this case, we're just using the note values of MIDI. And what this means is that the value of 60 is a middle C on the piano. So 60 is a C, 61 is a C sharp, 62 would be a D, 63 would be D sharp or E flat, etc., etc. 59 would be a B, and so on. So if you want to specify pitches in a more musically intuitive way, you can use M2F object. So if I just bring the volume up here a little bit, and swap over my outlet, we're hearing I think that's an A, a 440 Hertz number. If I click on 60, we've jumped to middle C, C sharp, and I can use a number box here to move up a chromatic scale. Yeah, that's what I'm talking about. So yeah, so M2F, useful object if you want to talk in more intuitive musical terms, if you know what musical notes are, of course. You could also probably get a MIDI files or something of tunes and feed those into PD as well. So now the implications of even what we know so far is actually quite profound. You can get quite a wide range of very interesting sounds out of pure data, really just using those basic building blocks that we've already looked at. So let me give you some examples of how you can combine some of these objects together to make some very interesting sounds. So we're going to start off with FM synthesis. So frequency modulation, or FM synthesis, you may have sort of heard of, perhaps. There's a very famous synthesizer called the Yamaha DX7 around in the 80s that made use of FM synthesis. And this is an example FM synthesis patch from this. It's one of the ones that's provided with pure data, actually. And it's worth spending just a little bit of time to take a look at what this is doing. It's really quite a simple patch if you look at it, but you can get some very interesting sounds coming out of it. So what we'll do, we'll start off looking down here. So we have an oscillator here. So that's a sine wave generator. And that's connected up to our output. I'll just bring the volume up a bit there, even though there's nothing on it just yet. And what we have here feeding into the inlet of the oscillator, we're setting its frequency. So when I drag this number up, we're setting the frequency of that oscillator. So we have this number feeding into a plus object, which at the moment is not actually adding anything, it's a plus 0. So we're adding 411, coming through that unchanged, setting the frequency of the oscillator, and then the oscillator's output going into the amplifier so that you can hear it. And we can also graph it as well if you want to see what it looks like. Now I'm just going to turn off the sound for a sec so I can talk without going insane. So that's our basic sine wave oscillator. But what we have over here is another oscillator. And what we're going to do is use this oscillator to modulate the frequency of this oscillator. So remember that what's coming out of these oscillators is all just numbers. So what's coming out of this oscillator is another series of numbers that are kind of tracing out a sine wave for us. And what we're going to do is take those numbers, we're going to multiply them by this number here, a modulation index. So let's just make that 1 to start with. And then we're going to, so that those oscillator values in the shape of a sine wave are coming out here. We're adding them to the frequency that we originally specified up here. So we specified 411 up here. And what we're going to be doing is adding the value of this oscillator to that frequency. So in other words, the frequency is going to be going up and down over time based on the values coming out of this oscillator. So we're using one oscillator to vary the frequency of another oscillator. So let's just bring up the volume. So at the moment we're not hearing anything different because this modulator is actually has a frequency of 0, so it's not outputting anything yet. But if I make this, hopefully you can start to hear the pitch of that oscillator vary now. Can you start to hear that pitch, vibrato in musical terms? So the output of this oscillator, which is now it's 3 hertz, so 3 times a second, it's moving the pitch of this oscillator down here, up and down. And the amount that it moves it up and down, at the moment I've only got it set to move it up and down a relatively small amount, but I can increase it. Now we're moving it up and down a whole lot. So that's going beyond vibrato now, that's starting to get nasty. So that's all pretty cool. So far we're really just playing a normal sine wave, but with a bit of vibrato, so a big deal. Where it starts to get interesting is if you start to mess with these frequencies of this modulating oscillator. Oops. You can start to get some very rich sounds coming out. Just bring the volume up a little bit. And so you can start to see and hear a very wide range of weird and wonderful sounds. Okay, too much fun. You can start to get a sense that you can get a very wide range of weird and wonderful sounds, really just from 2 oscillators. So very simple building blocks can create some very rich sounds, and that's why that Yamaha DX7 synthesizer that I mentioned back in the 80s was such a great value proposition for people, could be made relatively cheaply because internally they only had a few oscillators, but the way they'd combine those oscillators was very clever, and the synth could produce a very wide range of sounds. We can also take a look, so that's frequency modulation. That's where one oscillator is modifying the frequency of another one. We can also look at another synthesis technique I'll mention briefly here is additive synthesis, which I'm going to look at this one, I think. So we'll talk a bit more about this next time, but additive synthesis is essentially where you get several sine wave oscillators. Well, actually, they don't have to be sine waves, but you can get several oscillators really of any kind, but in this case, they're sine wave oscillators. And you just add them together. So you can see what we've got here is a patch where we're setting the frequency of this oscillator to be whatever the frequency of middle C is. And we're setting that to the output. Then we have another oscillator, another sine wave oscillator, but this time with a frequency double that of the first one. And we're feeding that through and adding that to the first one. And then we've got a third oscillator with a frequency triple that of the original one and feeding that in. And we're basically just getting all these oscillators and adding them together, literally adding them. So we're taking the values of those samples and adding them together, which is like mixing them together and sending them to the output. So instead of just one sine wave, we've now got 4 added together. So if I start this off, we'll start it off with just the single oscillator, so playing the middle C. So that's regular vanilla sine wave oscillator. And now I'm going to turn the other oscillators on. So you can hear that by adding these overtones, these other oscillators in, we've got a far richer sound.